one, you have to realize that this is the same thing as saying that x is greater than or equal to y. The next one is y is 2x, and then the other one's got the quick intercepts. Of the three of them, the first one I would graph is the last one, just because it's the one with the fractions on it. So as you go through that one, you've got x and y intercepts. Bless you. You wind up with x and y intercepts of 1/5 and 1/6, respectively. And then these two connect the dots with a solid line. Oh, I thought that was 0. I'm sorry. My bad. I didn't realize they were on there. So here we have to make them work. For some reason, when I looked at that, I thought that was a 0. So here we've got to do your 6y is going to be the negative 5x plus 1. Divided out by 6, you get this really weird intercept stuff. Okay? If you're doing that the long way, what you're looking at here is you've got an intercept of 1/6. Make that small. We're going up by 1s. Think of it this way. You have to go down 5 over 6. You're just kind of fudging your way through it. Go down 5 over 6. 1, 2, 3, 4, 5, 6. You're going to be down here-ish. Okay? That gives you that negative slope. Draw your line through. It just looks kind of weird. Okay? It didn't go through the origin, so is 0 plus 0 bigger than 1? No, so you're moving outward with it. Okay? Now the other two are basically just straight lines that go through the origin with different slopes. You have a slope of 1 for one of them, a slope of 2 for the other. So you've got your 1 over 1 slope going this way, and a 1 over 2 slope going, or excuse me, 2 over 1 slope going like that. When you start looking at those, you're going to pick values for what side are values of x bigger than y, on the right or the left? To the right. So this one's moving here. And then the other one, just pick any number, really. If I pick 0 for x and 2 for y, is 2 smaller than 0? Nope. So then that one's also going this way. It just looks really weird because of that. Okay. Now, what we use with these things for today is that we're going to do is we're going to use what are called, oops, it's out of sequence here. We're using linear programming. And what we're doing here is we're going to graph these shaded regions. And we're not doing the word problem parts. We're not creating our own objective functions or anything like that today. But what we're doing is we're going to create boundaries. Remember how in the past couple of drafts that I've done like this, I've thrown in and just not done that full shading, I've drawn some arrows? That's kind of what we're going to be looking at here today. We're going to figure out specific regions at which the graphs intersect that creates polygons, if you will. We're going to create quadrilaterals, triangles. We might not create something at all, but we're going to look for where these all these lines and stuff intersect one another. Another thing you're going to start to see a little bit more of is this idea of location of where the problem is going to occur. For example, in this first quick example, I say that x is greater than or equal to 0 and y is greater than or equal to 0. What quadrant does that occur in? 1. Good. So a lot of these types of problems become quadrant 1 problems. The reason being is that as we get into the word problem stuff next week, you can't have negative, like fruit baskets, things like that, all right? You can't have negative passengers on an airplane, all right? So a lot of these things become positive value only. So I'm trying to show you guys a little bit more of that today, okay? Now, what we do is that these things are now called constraints. These functions that they give you to graph to start with will be called constraints. What that means is that it's going to find your graph to a specific region. And you're going to be able to find the points at which the graph creates. Okay? So with these first two parts, knowing that x is greater than 0 goes to the right, y is greater than 0 goes up, that means we call it first quadrant problem. Sometimes you'll see just, x is greater than 0, you might not see y is greater than 0, That means it'd be in quadrant 1 and 4. It's little things like that that they start to show you. In a little while here, I'm going to have another example that'll have vertical lines. That might just be shifted over to create like a, I don't know, a cylinder or something. I don't think of it that way. Okay? And now the other ones, it drops you to the standard form. And remember when we use standard form, we use the quick graphs. Remember that, the cover and solve? We had people first hour going like this, but it's kind of funny actually. It works. Okay? So if I'm looking at this first one, if I cover up my value of x, what's my y-intercept? 5. If I cover up my y value, what's my x-intercept? Negative 15. Now, herein lies a bit of an issue, isn't it? My negative 15 isn't going to be the boundary that I need it to be, is it? So what do? You don't want to ignore it, but you just kind of fudge it that it's there. Here's why. Because if I still put this value here, that's still the x-intercept. Do you agree? And then I know my y-intercept is at 0 and 5. How many points do I need to make a line? That's why I know. Does that make sense by drawing that dotted line? Remember how we drew dotted lines sometimes to show that something's there that's not really there? That's kind of what we do. So I know that this portion down here doesn't matter. It doesn't matter until I get to here. It's going that way. Okay? That's where that line actually does occur according to the first two constraints. The x is greater than 0, y is greater than 0. And then you use a test point. Did it go through the origin? Nope. What's 0 plus 0? 0. Is 0 smaller than 15? I hope so. So it's shading downward. No, we've already talked. I already talked with him. He's good. Thank you for reminding me about it. Yeah, because we're on the assembly schedule. They're not. He would only been in class for 10 minutes. I caught up earlier. So right now, I've drawn the 3 arrows. It's kind of binding in that little spot right now. So I draw in my next line. What are the x and y intercepts from the last inequality? 6 and 12. Good. So if I put a 6 here and a 12 here, then I connect them. Did it go through the origin? What's 0 times 2? 0. What's 0 plus 0? Is 0 smaller than 12? Yes. So I'm moving inward. So what we've done here is that we've created this boundary here. What's that order pair at the bottom? 0, 0. It's the origin, isn't it? What's the only other point I'd have to figure out? This one right here. So if you think about what we've been doing all week, this section is a review of solving linear equations and shading, because it's all in one step. It's all the same. It's the same stuff we've been doing for the past 4 days. So it's just building into it. We're going to add one little piece to it here in about a couple minutes, but for the most part, what I need to do now is just figure out what's the intersection of those two. Now, when we're dealing with the intersection stuff, we don't worry about the inequalities at all. Okay? Treat it just like an equal sign for the equation and solve it like you would normally. And then you can go through any method. You can use substitution, elimination, or that linear multiplier, where you have to multiply and then eliminate. What's that called? Multiply to get something like this one. I have to multiply. If I multiply it by -2, what is it called? Linear combination. Thank you. I completely forgot what it's called. So you can choose any method you want. Let me show you what I do. In an example like this, everybody see how it's got a negative x? That means it's pretty close to I can just move the x over and I'd have x equals something, don't I? I would usually do that. Do I have to do it that way? Can I multiply it by 2 and add it to the other one? I can do anything I want. It works. But for some reason, whenever I see a negative x plus 3y equals 15, that means x is 3y minus 15. Just by moving stuff around. I can do that, or I can use the linear combination and multiply it by 2 and add it to the other. So knowing that my value of x is this, I just substitute in 2 times 3y minus 15 plus y is 1. I'm going to solve for the intersection of those two lines. And the way that we do that is that we just use what we were doing Monday and Tuesday. Okay? So let's see here. We get 6y minus 30 plus y 12. And one of the things that you'll know that you will come to find out with this section, a lot of the actual algebra that we wind up having to do is easier than what we did back on Monday and Tuesday. Same with the graphs. A lot of the graphs that we do from here on out with the linear programming part, because there's so many parts to it, they tend to be a lot easier to show. So, in essence, that part becomes a little bit easier, a little bit smoother. Okay. If you're still wishy-washy on it, by all means, please swing by in the morning, guys. Grab Flex Pass for next Monday or whatever. I know today we didn't have that, but couldn't, swing by before school. Okay. So if y is 6, what do you get for x? Yeah. You take this value, you go back up. And that gives me this ordered pair here then at 3 and 6. If I look at that graph then, how many points do we have that frame that shape? 4. We have 4 points that frame that shape, the points of inflection, if you want to call them like that. And what we do then is I want you to get in the habit of listing them. There's a reason for that because you'll see as we go on. It doesn't matter the order in which you list them. But these are the 4 important points of that diagram. What happens with that in a minute here is we're going to get something called an objective function. Think of it as, in word problems, a lot of times there's what we call a linear programming model. Those are the word problems where you're trying to maximize profits, minimize costs, put the most people on an airplane to sell as much as you can, where you're using multiple equations to get to something. And those shaded region areas are what creates your possible range of values. The objective function tells you where you're going to get your best bang for your buck. Okay? That's where that comes in. Get that out of your teaching, please. Thank you. So you get to stuff like, eventually, stuff like this. I'm going to pick one really straightforward to start with. I'm not using graphs. Oops. That's another one. We're going to find what's called the maximum and minimum of an objective function. Today, these objective functions are going to be given to you as this thing called C equals something. The reason that a lot of times they use C is because, like I was just saying a minute ago, some of these functions are generally profits. So think like costs and stuff. I think that's why they use the letter C. Otherwise, I'm not exactly sure. But today, in the problems that we're going to do, this objective function will be given to you. Next week, when we start building into the word problems, you're going to be developing your own objective function. And it sounds really weird, but it's actually pretty easy to do because when you read a problem, it'll tell you, in order to maximize profits, in order to maximize sales, something along those lines, you're going to be able to take information from that to create it. Okay? It sounds weird because you haven't heard this before. So what we're doing is that we have this objective function, C equals 3x plus 4y, and it's subject to the following constraints. Oh, I'm sorry, I didn't blow that up. It's subject to the following constraints. X is greater than 0, y is greater than or equal to 0, and then x plus y is less than or equal to 8. Really quick here, what quadrant does this work in? 1. It's only on quadrant 1 problem yet. Okay. We know it's quadrant 1. Another person asked this during first hour about with these things, do you see them a lot of times with less than symbols? Not really. It's very rare with a lot of these things. You're going to see less than symbols for the objective functions because you want to create an actual region. If you have a less than symbol or a greater than symbol, you can get infinitely closer to it without being there. So a lot of these things will be equals. And then the last one, what are your intercepts? 8 and 8, very good. And remember, when we're doing these things, I'm trying to just visually represent it. I am not counting anything. I'm not tick marking anything over to how far I'm going. I don't like using graph paper for this stuff at all because it's much easier to do it without. So these past 2 days, if you've been graphing stuff without graph paper, and you've been like, oh, it's not that bad. Sweet. Okay. If not, come get some help. What direction are those arrows going to point? Towards the origin, right? Because 0 plus 0 is smaller than 8. Which means this is my last little ordered pair. What did we create? Yeah, thank you. Yes, in this example, we did create a 45, 45, 90 triangle. Very good. I wasn't thinking of that, but yes. What's the length of the hypotenuse? 832. Very good. So what you do here is that, see how we've got those 3 points of inflection? All we have to do now is list them. We list those 3 points out. We had 0, 0, 8 and 0, 0 and 8. And what we're going to do is we're going to take these values of x and y into the objective function. So 3 times 0 plus 4 times 0. Where this comes from is if you're selling 2 different objects, let's say you're selling keys and pens. And it's a strange combination. If I get $3 per set of keys and $4 per pen, what am I going to make the most profit at? Well, it depends on how many things and what my constraint is. What is my supply level at? You only can sell so much of what you have. That's what they call it a constraint. That's where the stuff leads to. Right. It's actually pretty useful stuff. So what's 3 times 0? 4 times 0. 0 plus 0. Sweet. Okay, there's one answer. 3 times 8. And 4 times 8. Where is your minimum? 0, 0. Where's your maximum? There you go. What values give you your minimum? What values give you your maximum? Here's your min. Here's your max. And depending upon what the ordered pairs meant, if it meant keys and pens, meant sell no keys, sell all the pens. You'll make all the money. It's kind of where this goes to. Okay. Apparently ones that nobody needs. Meaning it's keys for luggage because you can't put luggage locks on anymore because they're going to break them open anyway to make sure you're not smuggling. You want us. Yeah, you can't put luggage locks on things. 2,000 and more. With the airlines, they don't always have locks on them when you check the bags. They come off. Oh, well, you got lucky then, because I know that when I brought last time I flew, they always come off on us. Yeah. What's that? Hey, don't you smuggle? Haven't you smuggled an iguana lately? You haven't lived until you try to smuggle an iguana. You know that they get. Yeah, right. All right. I know that we're going to be losing people here in about 5-6 minutes, so I want to try and get through a couple more of these as quickly as we possibly can. If you do miss out on some of these things because you got to bail out, I understand. Homework's posted. The notes from first hour are already posted, as well as the stuff for tonight. I'll have it posted before we get out of here as well. But what I want you to notice here is, in this case, if you have x is greater than or equal to, x is less than or equal to 5, y is greater than or equal to 0, what quadrant do those 3 things put you in? It still puts you in the first quadrant, doesn't it? But creates a certain boundary within the values of x. It creates certain boundaries for the x values there, doesn't it? So when we draw this one out, in your mind, you should see, hey, these first three things tell me that I'm still first quadrant. It's fine. Okay? I still know I'm first quadrant. When I have x equaling a number, what kind of a line is it? Thanks. Sure. Vertical. Vertical. Okay. It's a vertical line. So it's going to go through 2, and then I have another vertical line at 5. So vertical line at 2, vertical line at 5. What direction do I have to put the arrows? Towards each other. Greater than 2, less than 5. So they're pointing at each other. They're being very rude. What's that? And then obviously we're moving upward. Everybody okay with that so far? What are my two bottom points then? The two bottom points of inflection. Very good. 2, 0, 5, 0. Everybody okay with that? All right. So sometimes you're just going to get information like this, where there's no lid on it. What I mean by no lid on it is that there's no boundary at the top to cap it off. So would a problem like this have a maximum? No. Could it still have a minimum? Yeah, absolutely. Now, what happens if the graph was like this? Well, all right. What happens if it had boundaries at the top but nothing on the bottom? And then it could have a maximum but not a minimum. What I'm meaning by that, I know this is not how it would look. I just spun around because I thought it'd be kind of silly. But what I mean is that sometimes you will not have a maximum value, but sometimes you won't have a minimum. Okay, that's what that means. Okay. This next graph is in slope-intercept form. But as you guys know, sometimes if you don't have graph paper, slope-intercept form is a bit of a pain in the butt, isn't it? What would I do with that negative 2x and put it in center form? Add to the other side. And then you can do your quick solves, don't you? If I do that, then now I've got those quick cover and solves, and it's much easier to graph. Because I don't have to worry about trying to count off and go up to 12 and do all that other junk. Here I can just say I have an x and y intercepts at blah and blah. Well, my x-intercept is where? 6. Very good. Where's my y? 12. So 6 is here, and 12 is here. Connect them. And what direction does it have to be shaded then? You're right. You're right. You're right. You're like, yes, inward. Yes, very good. All right. So you're shaded inward, which means you have 2 more points to figure out. But notice, you already know one of the coordinates, don't you? What's the x-coordinates for the one vertical? It's 2, because it's a vertical line. So you have a 2 here, and you have an ordered pair here at 5 and something. Well, if 2 is x, what's y? 8. 8. 8. Y bueno, pues va a ser igual acá. Muy importante. And then if I do 5, ¿tú hablas español? Oh, lo siento. ¿Tú no hablas español? Lo siento. Oui, un poco. What's 5 times 2? 10 plus what is 12? See how we're using the systems of equations within these types of problems? It doesn't change from earlier this week. There's methods to the madness of the things that I'm trying to show you guys because I'm trying to build into other stuff. All right. So now we have our 4 points. I know some of you guys got to bail. I totally get it. You have your 4 points. You've got your 2, 0, 5, 0, 5, 2, and 2, 8. People have asked me about this. Is there a reason why you listed in some specific order? No. There's no reason for which points you put first, which order you put them in. As long as you know you have 4 of them, you write 4 of them down, I'm happy because that's what we need to do. They don't need to be in any specific order. For some reason, I usually start at the bottom left and just work my way around. Yes, ma'am. How do I get 8 and 2? I mean 2 and 8. What happens here is that you've got the vertical line here at 2. So vertical line at 2, that value of x never changes. Oh, the y for this? Oh, for the 8 value? Oh, since this value here, where it intersects it, the x value has to be 2. What I did is I took the value of 2 here, 2 times 2 plus what is 12. You're using that system of equation where, remember, where they intersect each other, they're going to share a coordinates. If you know one of them has to be 2 because it's vertical, it's a quick substitution. Also, you're going to see some of them where I'll have a horizontal line where you'll have a y value known, and then you substitute to find x. It's just one of those quick substitution things you just know. All right? That's why I kept harping x equals number is always vertical, y equals number is always horizontal. There really is a reason why I say things, not just to say them and waste your time. From there, it's just about... Like I was saying, at this point here, you just have to substitute through. So negative 2 plus 0, negative 5 plus 0, negative 5 plus 6, and negative 2 plus 24. That gives you your specific values to be able to determine which one's your maximum and minimum. So you get... From there, which one's the biggest, which one's the smallest? Yep. So if this was a maximized profit one, let's say you lost $1 on every pen, but you made $3 on every key. I guess I'm going back to pens and keys because that's what I had in my hand in my pocket. All right. There are things that stores that people lose money on. But for more often than not, it's commodities. You guys know what I mean by a commodity? 2x4s, drywall. They don't make any money selling a piece of 2x4. What they make money on is they make money on the nails and the screws and stuff like that. That's where you ever heard of margin? When you sell something, if you wanted to sell me your notebook, how much did you pay for that notebook? Let's just say you spend $2. All right, you spend $2 on that notebook. What are you going to sell it to me for? 15 shouldn't be shut. Let's be realistic. $6. So that means that your profit, you're trying to make $4 per notebook. But that's the idea. You're buying stuff at a specific cost to resell it later, and that's what we call your profit margin. It's a certain percentage above what you bought it at versus what you sell it at. Certain things have different profit margins. Okay, that's where this stuff comes from. All right. That's how you go. Make you stand. All right. Smack you next to my toes. Not this one. Not this one. This one. I know I'm running really short here, and I think this is as far as I got in the first hour as well. Let's try this one. Okay, let's try this one out. I don't have this one out. I know, but I want to do this one and start one other. I didn't say that. I never said that. I just wanted to make sure I got this part, like, just a little bit further. What's that? I share it.
I don't want it.
I know they say caffeine. It's not the caffeine that's bad for you, it's the aspartame that's in this stuff is what's going to kill you. You got me a bit sick. Have a good weekend. Homework's already posted, everything's there. I think I got like 6 of these, I think. I would be, yes. Since we're running a little short here, what quadrant does this happen in? 1. Are we okay with that? All right. We're in quadrant 1. All right, we're quadrant 1. First graph, where are your x and y intercepts? 5s, good. Does it matter where I place the 5s? Nope, as long as I label them. Connect the dots. And which direction does this go? Does it go up or in? It goes up, doesn't it? Because 0 plus 0 is not bigger than 5, so it's moving outward. We okay with that so far? All right. Next one, your x and y intercepts are where and where respectively? 6, 0, and 9.5. 9.5 is what? 4.5? Okay. So if I put here, it's you can use it. It's. I don't personally like decimals, but when I'm graphing something, if I just say that it's here at like 0 and 4.5, is that okay? It's close enough, right? What I'm doing is getting just a quick visual, and then I just connect them again. Oh, they ran into each other, so that might be important. And then again, did it go through the origin? Nope. So what's 0 plus 0? 0. Is 0 bigger than 18? Nope. So I'm moving outward again. So in this problem, we dealt with a region here, here. Is there going to be a maximum for this region? No. That's why I wanted to show you guys what something might look like with a no maximum value. This would be a case that there's no maximum. The reason being that there's no lid on it. There's a floor, but there's no ceiling. Okay? There's a floor, but there's no ceiling. But I still have to figure out that ordered pair. That ordered pair occurred where these two guys intersected. Didn't it? Now, that goes back to the same thing we did back on Monday and Tuesday, but it also becomes a little bit easier because you'll notice the graphs or the equations themselves are pretty easy to work with. When you solve the systems to find the intersection points, remember, totally disregard the fact that it says greater than or equal to or less than or equal to. All you're doing is looking for where they do actually equal, so you just set on the equal, or not set equal to, but you're going to use elimination, some of those methods. In my mind, I'm thinking, okay, just get rid of x. What do I multiply the top equation by? 3. So what I would do is I would multiply the top one by 3 and write it below. 3x plus 3y is 15. Subtract everything. And look how fast you get a value of y. Everybody see that? You get y equals 3 really, really fast. And then, what's x? 2. The system of equation stuff that you did back Monday, Tuesday, the graphing of the inequalities you did Wednesday, Thursday, were a lot harder than what these are. Okay? It just so happens that they're all in one problem. Okay? That gives me the ordered pair then at 2, 3. So I have 3 points to check. 0, 5, 2, 3, and 5, 0, and I forgot my thing. 5x, 6y. So 0 plus 30 is 30. 10 plus 18 is 28. And then 25 plus 0. Oh, not a 0. I'm sorry, this should have been a 6. I'm sorry. That was supposed to be a 6. Sorry about that. I looked up and couldn't read my own handwriting there. I apologize. We know that there's no maximum because there's no ceiling. But where's our minimum then? At 2.3 at 28. Bless you. All right. I know I'm kind of hard to yell at you at the beginning of the hour. I didn't really mean to get mad at you guys. I wasn't mad. I know, exactly. All right. I had one more. Oh, that's right. All right, we'll stop there then. We'll finish these out. It's on the calendar. It's 3.4. It's on page 166. It's 12 through 20 evens. You'll notice that they give you the objective function. They give you all the constraints. Don't use graph paper. All right? Don't use graph paper. I think the most you have to graph on there, like 4 of them, and usually those are when you're making like a rectangle. All right? It's really straightforward. Monday, what we'll do is we'll go through these again, make sure we're all right with them. If we need time to spend another day building our graph before we do the word problem parts, it's fine. Because the word problems, I've already planned on those probably takes at least 2.5 days to get through. And people always go, "Ooh." They're not that bad. It'll be fun. Okay. I know that a lot of times when we get to the word problems, I finally learned after last year to actually have a copy of some of them for you as I'm talking about it, so you're not trying to write everything down right away. So you don't have to write out 7 sentences about all of it. So I actually I already have the couple of the first 4 or so that we're going to do together. So we'll be able to get through a little bit more of them as far as examples are concerned. I'll show you guys how you highlight or underline specific terms, what to look for. And then if you can build, if you can graph these things, word problems are cake. Because you learn, it's a first quadrant problem because I don't want to lose money. I can't have negative people. I can't have negative shoes. I can't have negative fruit baskets, things like that. And then you start to realize, okay, there's a cost and there's a product. Costs go together, products go together. You have a certain amount of money to spend and you have a certain amount of products to sell. That's kind of how things build out. It's just a matter of keeping things straight. Yes, sir. Yes, sir. Okay. Remember, if you got questions or things are starting to get late and all that, swing by first thing in the morning or grab, past 2 days we had to flex, but if you need one already for next Monday or whatever, please grab one. Help yourself, okay? We'll be here. Unless I'm dead. I don't think so. Probably be the caffeine. It'd be somebody running the